Hello robot friends, today I'm doing a full review of this Asimov robot that was released by a company called Menlo Research based out of Singapore, and they before have been releasing the lower body, so feet, legs and hip, but now you can see the whole thing, which is amazing and is in pre-order, so you can order that. And they've released a bunch of videos which looks very promising, and there is a great team behind that. So if we look at the actual video, I'm going to take a look at this.
Asimov.
Okay, the first thing is that I'm not sure if it's a speaker or an inductive charger. Maybe it's a speaker. It reminds me of Iron Man, the core, but
A new open source humanoid that's now available for pre-order. A team from Singapore-based Menlo Research has been building the robot publicly for months, while throwing shade at China's Unitree, which leads the world in human.
so it is a competitor for the Unitree G1, which is what I'm going to do in my slides later. So I'm going to provide a comparison and reference to the G1 because that's what they say.
Humanoid deliveries. Asimov ships unassembled for Earth.
It's unassembled, guys. You have to build this. Look at that. I would love to build this. I understand they will give you all the parts, which is can't tell if it's CNC machine, aluminum, steel, or polycarbonate, but the material is quite important, as I will explain later.
Early adopters. Standing 120 centimeters.
That's the height, so toes to head 120 centimeter.
Or just under 4 feet. The humanoid is a bit shorter than Unitree's viral G1.
It is.
Which has soared in popularity among researchers and developers since its launch
What
in
was that?
2024.
Let's Bruce
When
Lee.
assembled, Asimov weighs 35 kilos or 77 pounds.
I'm assuming that's with the actual battery pack, right? I think it should be the battery pack.
And boasts 27 degrees of freedom.
That's amazing. That's a foot joint, which is very new, right? I haven't seen that before in a robot, humanoid robot. I mean, I've built robots with that mechanism before, but not in a full humanoid robot.
Pre-orders require a $500 deposit. The targeted price is around 15 grand, about the same as the G1's entry model.
Okay.
However, Asimov is fully open, with configurability only available in higher-end Unitree models. This is
great. So yeah, the video is amazing, and yeah, I'm really excited to see this. I won't have the money to buy one, of course, and from these pictures, you can see there are no hands, and I'm not sure what have they decided, if they are going to make the hands as well open source, or they're going to use Anko's hands, and I will show you in my slides what do I mean by that. These parts, I mean, I'm assuming these are aluminum or steel. These are definitely Anko motors, and these ones maybe is plastic. And it's very important because of the specs. They're talking about 15 kilos per arm, bicep curls, and 18 kilos for lateral raises. That's a lot. He needs to, I don't think he can do it with that with plastic. Just the heat is going to be so high that it's going to melt the plastic. So yeah, this is interesting. That's the front. I can see there is a hole there. Maybe the battery is behind that. I'm not really sure what's in there. The cables coming out, and those are the motors. You can see. I love this. I have the same hammers. These are quite nice. Those are the legs. Yeah, it looks like it might be a combination material. It is not specified. I'm really curious about materials. So what I'm going to do next in the next section is to have a PowerPoint. I know nobody was like PowerPoints, but there is so much information that I had to collate it into slides for for just to be more clear. And here we go, slides. This review was made on the 7th of March, so just keep that in mind. That's my Twitter profile. Please follow in for further updates. First of all, just quick specs. 1.2 meters height, 35 kilos. I'm assuming the battery is included. Maybe not the hands. I'm not sure if hands are part of that 35 kilo figure. 25 plus 2 degree of freedom. Humanoid robot. So I think, I'm not sure if those are the legs only or the whole body. Let's check it out. Comes unassembled, full manual and build videos included. Shipment starts in a few months. Target price 15,000, and yes, you have to provide a deposit, of course. So I think 2 degrees of freedom maybe is the full joint, and then 25 is everything else. But let's see. First of all, the name Asimov. Well, it's a famous sci-fi writer. I like him. That's why I went into robotics, to be honest, and probably most of the people out there came from the same background. He died when he was 72. I remember that in 1992. So if you haven't read any of these books, I really recommend reading the Foundation trilogy, which was also featured in a movie, but the movie was really bad, so don't watch that. I'm going to go for a trivia since you're talking about humanoid and open source. Do you know what was the first open source humanoid robot? I'll give you a few seconds. And I'm so proud to say that was made in Italy through a research group, as we call it, a consortium of research and commercial bodies. And it was released in 2009, which is many, many years ago. Now we're in 2026. So it was really a feature of engineering and software development. It was very cute. It was supposed to mimic this 3.5 years old. I believe this project is still active, and I will try to reach to one of my ex-colleagues because they have a lot to share about how difficult it is to develop a humanoid robot. So go and check it out. The company itself is Menlo Research. Originally, to be honest, I thought they were based in the Silicon Valley because all these humanoid companies are either in Europe or in the Valley. But this is based in Singapore, so kudos to them. I like to see more Asian companies in this area, and they have employees 11 to 50, it says. And they also do other things, not just the robot, but other platforms around the actual humanoid robot. If you look at the vacancies, I like to look at vacancies because just to see what they are hiring for. And they seem to be quite active. So they have internships and robot engineers in Singapore, but also in Vietnam, in Ho Chi Minh City. And I've been to both cities, and I like them very much. It's great for holiday as well, to be honest. Look at the weather now in the UK. It's terrible. So, I mean, go and work for them if you want. It's my advice. So let's talk shops. Just looking at the actual legs, I can only see the legs information for now. That's why I'm going to do that. So they have 12 degree of freedom, so it's 6 per leg. And they have an articulated toe, and it can lift 15 kilos, but not the actual legs. The actual arms can lift 15 kilos, but it's very important for the legs as well, because you need to support that torque, right? When you're lifting so much, and it's quite a lot for a robot of that size. So the ankle is an RSU. I built that before. I don't think it's super innovative, but it makes sense to be in an ankle. I mean, that's what people have used it before. And the actual motors are from a company called Ankos, which I never used before, so I want to dig into that. I'm going to give you another trivia now. Who holds the world record for a strict bicep curl? And I'll give you a few seconds. Well, the answer is Da-da-dum, da-dum. Leroy Walker from the US and another person called Nizami Tagiev. They were able to do a street curl weighing 114 kilos with a body weight between 110 and 145 kilos and their height being between 183 and 188 meters. Which is quite impressive. I'm 70 kilos. I go to the gym. I'm not a weightlifter, but I can do a 15 kilo per arm street curl. And yes, it's a challenge for me. But these people can do almost, a ratio equal to their body weight as a street curl. And of course, if you do a cheat curl, you can do a little bit more. So there was another person that managed to do 180 kilos, basically the same as his body weight. So as you can see from this person here, it's not just the arms, right? You need to have a very strong body overall to be able to sustain that torque. Otherwise, you are essentially like, even if your arms are super strong, like you can keep your body on a straight line and you will basically just collapse. So what will you need for 15 kilos straight curl? Based on the Asimov weight of 35 kilos, and if you have a payload mass of 15 kilo, which is what is lifting, I'm assuming both arms in this case, or let's say one arm, like symmetrical. And if the arm is 0.4 meters, because I don't know from the specs, and the torso height is 0.6 meter, and the foot are like 10 centimeter, you need to lean, right? So there's no way you can do that with a robot of that size and weight. Even if the arms are super strong, it's going to face plant on the floor, as we have seen in other competitions. And so it's very important to have also strong torque motors on the hip pitch. So you will probably need like 55 Newton meters, and also you will need something like at the ankle of 60 Newton meters. This is just like my simple calculation, and you will need to essentially move like sort of lean back 16.5 degree, which is what humans also do, right? I mean, you need to counterbalance that leverage with your body. So 15 kilos is a lot for a robot that is 35 kilo. I really want to see that in a video if they can release that. And so if we compare that to the Unitree G1, the base version can do lift 3 kilo, sorry, a 2 kilo, and the educational version can do 3 kilos. So it's a massive gap between the Asimov and the Unitree. Plus, they also claim a lateral raise of 18 kilos, which I haven't done any calculation for. But it's overall, this is, I'm really excited. And the other things, obviously, is the peak joint torque. You need to have that power, that torque to be able to do that. And there is a 120 Newton per meter spec, which I'm going to investigate. So how can you do that? Well, they released the MJC, so the actual file for Mujoko. You can load it, and this is the Mujoko XML viewer. And you have the mesh, so you can actually see the lower body part. And you can play with that. I can share my screen later. They didn't release any models for the URDF format, which is pretty good if you have to do reinforcement learning or imitation learning of some sort on multiple GPU cluster, because you need that power of running multiple robots simulations. But I don't think that's a big problem. You can probably convert it from the MJC to the URDF, but for now is not available. They release step files, which is good for CAD design or modification. So if you want to do machining, you can actually open these and see the full specs, and it looks pretty well done to me. I can also show you how you can open that in my browser. And now let's talk about legs. The only things we got for now are legs. So the left and right are identical. That's not always true in humans. We always have one leg that is stronger than the other one. But in robot, you can have perfect symmetry. It doesn't really make any difference. And they have the hip, the knee, and the ankle. They don't mention the foot joint in this table. This is from their website. Maybe they forgot. I'm not so sure. But you have then, so you have essentially 1, 2, 3, 4, 5, 6. So you have 6 degrees of freedom per leg, plus, I guess, the foot joint. And you can see that the peak torque, so the strongest joint, let's say, is the hip pitch, which is the flexion and extension in human terms. And it's 120, and then you have the 90 Newton per meters on the roll, and then you have the knee pitch, 75, there's only 1 degree of freedom, followed by the yaw of the hip and the ankles. All the motors are specified here. You can go and check them, which I did. So how the kind of hip detail works, I mean, in a classical robot setup, this is not from the robot, it's just for illustrative purposes. You have 3 degrees of freedom, so you have the pitch, which is kind of like the upper leg femur, so where you do the, the sort of your swing, right? So that's the pitch rotation, then you have the roll rotation, right? And then you have the yaw rotation, which is the green axis. And so the pitch is anterior posterior rotation, the roll is the medial lateral abduction, and the yaw is the rotation on the vertical axis. Now, depending on your coordinate frames, I mean, this could be, usually Z is pointing up, but, you can swap this axis. It doesn't really matter. It depends on the actual controller, of course, and how they implemented that. If we look instead at the actual foot or the ankle, sorry, they have 2 degrees of freedom only. So you have the, you have the kind of ankle pitch, which is the dorsiflexion and plantar flexion axis in red. And then you have the yaw actuator, which is the, that one that sort of does the medial lateral eversion inversion. That's not in there. Sorry, they don't have the roll actuator, right? And I'm getting confused myself, but they have 2 axes. So they have the ankle pitch with the dorsiflexion and plantar flexion. And they have the ankle roll, so which is the inversion and eversion axis. And I mentioned them here. I should have put it there. So they have 2 degree of freedom with minus 70 and 70 degree, which seems quite high. And we will see why this is a little bit odd. So they don't have the roll actuator, meaning that you can't sort of move your feet like that. And we can see that in the actual model file, that's why it's not possible. Still, that's quite impressive. This is not from the representation, it's just to kind of explain that potentially you can have 3 axes, but most robots have only 2. Which is not a big problem, but of course there are some things you have to consider during the inverse and direct kinematics. Okay, so the motors themselves, they are designed from a company called Anko. So they are designed and manufactured by a company called Anko. They are based in China, in a city called Jian, in the city of Nanjing. I think I've actually been there. In the past, I used to do a lot of business in China, and especially PCB manufacturing. And I also work with some robotic company, but I never used their motors before. So I can't really sort of talk about the quality of the actual machines, but if they've chosen them, they're probably pretty good. So I'm going to pick just one of the motors, the most powerful one, which is the one on the hip. So it's the strongest motor on the hip, as we mentioned before, is 120 Newton per meter, has a weight of 805 grams. And so, well, as we said before, why it's very important, because probably if you're doing something very heavy, the hip is the one that is going to do a lot of the work to counterbalance that weight. So if you look at this, I mean, you can go on their website, and I only took some of the most important specs. So you can control it via CAN bus. The CAN bus is the same one you have on your cars. You know, it's a data protocol used to exchange information between sensors and the ECU. There's double encoder, which is pretty good for providing safety. As you can measure very accurately the difference between the, if the motor is under stress and there's an external force, the mechanical joints are bending, so you can actually see the difference between an obstacle and how the gears are sort of stressing out in that direction. Of course, you have to know the efficiency, 73%. The P torque, we know that. The peak phase current 60 ampere, which is essentially the maximum you can achieve. So you need to make sure you don't you have to limit your supply. The speed, the power, 624 watts, so it's quite a powerful motor. And the kind of voltage, so 48 volt is the same as the Unitree, which means they're probably going to have a battery with 13 cells or something like that. But I'm not so sure yet. I don't have any information. So the motor looks pretty good. If we compare that with the Unitree, the strongest joint in their design, which is very interesting, is on the knee joint. So as you know, as you get old, the knees are the ones that are also very painful because, they support most of the weight. And when you run, don't run on the concrete because it's going to destroy your joints. I don't know why people run on concrete. You should run on something soft. We were not designed to run on concrete as humans. But anyway, I think their selection is to have a strong knee joint. It's a design choice. On the basic one is only 90 Nm, but on the educational one is 120 Newton per meter. And the movement range is 0 to 165 degree. Remember, this is the knee joint. Okay. And the motor type is PMSM, which is the same one as the Anko ones. Dual encoders, same as the Anko ones. And the cooling is localized air cooling. I haven't seen any cooling specs on the Asimov, and I hope they have. I mean, I couldn't really see it. Maybe it's built into the motor, but I don't have any information on that. And you will see why this is very important. And the gear bearing is cross roller bearings, which is the same as the Ankos. So let's go next. Just to give you an idea, so joint mobility is also very important. And why it's important is that obviously humans, they have joint limits, but if you're a robot, maybe you don't care. You want more joint mobility. You want to do something with more dexterity. Maybe it saves you some energy. So why not, right? And so I made a quick comparison. So between the G1 and Asimov, so the hip joint, they have minus 154 to 154 for pitch. So actually Asimov have less range. Roll is minus 30 plus 170, so it's quite extreme, and I can show you why. And the yaw is 158 both ways. And Asimov has 45 either side, so it's definitely limited in range. I don't know why. That's a good question for them. Because the motors can have more, of course. The knee joint is just the knee, and the Unitree has even more range, 0 to 165, and the Asimov has like 0 to 86. On the ankle, they have also pitch and roll, as I mentioned before, and it goes between minus 50 and 30 on the pitch, and on the roll is minus 50 to 15. But Asimov on the ankle has minus 20, 20 on pitch, and minus 5 to 5 on roll. And I don't know why this is different. I've seen in the specs minus 70 plus 70, but if you actually go into the simulator, if you visualize the actual model, it's far less. So I'm not sure if there was an error there, or is the theoretical limit, and then they sort of mechanically restricted that. But it's lower. I mean, I don't think it's a big problem having these limitations. I think this is a little bit too much anyway. But yeah, I just want to make sure people understand that. Okay. And so how does it compare to some human spec, right? Like 35 kilos average person. And there have been a lot of studies about biomechanics, which I can go into details in another tutorial. So people have been measuring the peak and stall torque for people of different ages, different height, different sex, like male and female. And I don't know if there is anything. I think there's also some studies on ethnicity, because they change incredibly. So just to give you an idea, I mean, if you were a human of 35 kilo, you have these normalized measurements. So you will do on let's say, the hip pitch flex and extension. You will typically have like 2.5 to 3.0 newton meters per kilo. So you'll have to multiply that with a peak torque of 105 on the hip, and the pitch, and 75 as a stall. Yeah, that's something to consider. And you can see that, as I mentioned before, the knee pitch is the one that has more peak torque. So this is very interesting. So the Unitree, in my opinion, is more like humanoid inspired, because you have a higher peak torque on your knee, but the Asimov has a higher peak torque on the hip, let's say. So a very interesting design choice. I'm sure there is a reason, and I would love to talk to them about that. And the ankle as well. I mean, the ankle are also very important when you run, or you go upstairs or downstairs or on a slope. So they also need to have a good torque power, right? So obviously, because they're smaller parts of your body, they have kind of lower ones, but you can see that the dorsiflexion is actually higher. You have 42 newton meters compared to the ankle inversion. So yeah, I think it's something interesting. I like biomechanics, and because these robots needs to perform similar tasks to humans, supposedly, evolution has given us some advantage in terms of structure, and so it's a good reference. But I guess it also depends on the kind of robots and how they are designed. So if we just want to compare it, sort of overall quick comparison. So the Unitree G1 is 13,500 in price. They do have a battery. They do have vision, so they have a 3D LiDAR and a depth camera. It's 23 degrees of freedom without hands. The weight is 35, yeah, like Asimov, and the height is 1.32, so it's a little bit taller, as they say. With Asimov, you have $15,000. I'm not sure what the battery is. I suppose it's included. There is no information on the vision module, so I don't know what's that enticing. And you have 25 degree of freedom plus 2, so 25 in total, plus 2, I guess, is the foot. And the hand, I don't know what's the hand going to be. I'm guessing will be like the Ankos, and Ankos also sell and end module, which is the same one they produce the motors for. The Unitree G1 educational version, they have different configurations. So depending on the kind of hand, you can have between 23 and 43 degree of freedom. Yes, they do have the same modules. They weight a little bit more, I guess, because of the hands, and have the same height. And the hand is this DEX-free one, free finger force control. All right, so hopefully that sort of give you a nice indication of the capabilities. Let's go next. I mean, this I generated this is kind of like from Gemini, but just to give you an idea. So the Asimov is 1.2 standing height. The Unitree G1 is 1.32. They have this 0.6 leg length, which is 45% of the total standing. So why I'm saying that? There is a very important measurement from biomechanics called the Cormick index, which is essentially the proportion between when you sit in a kind of like fetal position versus when you're totally standing. And that's very important for kind of balance and efficiency when you are essentially running or doing some lifting. So I'm not sure what Asimov. I will have to see the entire specs. I mean, I could calculate that, but I didn't want to give any information now. And yeah, they both have the same weight. The ratio, the leg length ratio is 0.6. And so the stability is very important because, depending on when you put your battery, your center of gravity is really important. And you also want to have like a feedback control loop that is fast enough for balancing and all other tasks, which we don't know yet. But yes, the center of gravity or center of mass is very important, and it does change. So when this robot move his arms up and down, the center of gravity, center of mass change because the arms also have weight. So like overall, we'll have to see how the entire model stands in a simulator to kind of measure a little bit more details on the balancing capabilities. So foot control, I like feet. And so I took the actual model kind of to see how they look like, and they have a very similar structure to the Unitree. So you have the pitch joint and the roll joint, yeah, left and right, you can see them. So this is the Unitree and this is Asimov. And the actual actuators, the joints are on the, let's say, lower leg, right? On the thigh of the leg. And they have like this metal, well, I'm assuming will be rods, as you can see them here, that connect the actual spherical joint. So you don't have motors on the ankle because, people have discovered that they break. And I can tell you that they break. I've built robots with joints on the ankle, and they break quite a lot. So that's why you have two rods connecting them, which makes sense. So I don't see any innovation on that part. But yeah, you have the rotational joint on the front foot, which the Unitree doesn't have. Okay, so why I like this? Before I go into some sort of more discoveries, obviously it's made in Singapore. I mean, I want to see more diversity in the humanoid space. It's totally open source. There is this amazing foot innovation and more torque. I mean, it's I just want to see, like, if you want to do something useful with robots, like lifting a shopping bag, you can't have 2 or 3 kilos, lifting power. You need something like 10 kilos. When I do my shopping, I think usually it's 10 kilos. Just for food. So if you want the robot to bring your shopping, you need to have that, right? Even if it's sort of doing a penguin walk and moving your shopping bags. But there is not just the actual hardware. So they offer also the Asimov OS, the operating system that runs on humanoid robots. This is interesting. Maybe if I have time and to test it, it's something like the ROS operating ROS. Maybe they have their own version of that. Then they have the humanoid robot, okay, which is the one we described today. And they also have a supply chain, so means you can essentially, I guess, if you are an OEM or a manufacturer, you can say, hey, you can be, you're compatible, so you can build a robot with those components. But yeah, supply chain is very important, because if some of those vendors go belly up and they go out of business, then you can't build a robot anymore. So yeah, so that's kind of important. Now, unknowns. So what's the battery size? Is the final price 15,000 including the the battery and the maybe the vision system? Like, does he have a vision? I'm not so sure. Hand selection. So yeah, what's the desired hand? I know you can put your hands, but what will be the kind of default choice, right? I want to know that. Vision, yeah, as I mentioned. So how do I mount vision on the head? Like, what modules can fit in? When are we going to have these Isaac Sim specs? Because for people that want to do some reinforcement learning, parallel training for locomotion development or VLAs, you do need to have those ones. And what's the choice between material and motors? Because materials are everything. Like, when you look at this pancake, I just had breakfast. I had a couple of pancakes, but they're called pancakes because they are flat and they are a good design. But they heat, right? And like a 48 volts, yes, you can calculate the peak torque, but as you push more current into this motor, you're going to dissipate heat, and the heat usually comes exactly from the sort of mounting points or the actual motor. And if you look at different materials, I have a 3D printer here. I do PLA. That melts at sort of 60 degrees. So 60 degree is the actual temperature of my bed plate, right? So which means it sort of allows it to kind of stick, but it's like in a sort of semi-fluent state, right? But when you go from 20 degrees ambient temperature in the UK, it's a warm day. But if you're in Dubai, it's going to be higher than that. But so when you have plastic at 80 degrees, PLA start to soften, right? So my nozzle right now, well, I usually print at 198 degree from the nozzle to make it fluid. But at 80 degree, which is a quite common temperature if you have on high torque, is going to melt your PLA, right? It's going to deform it, and you're going to lose accuracy until it breaks. If you have a PETCG, that starts at 80 degrees, so it's to be higher. If you have ABS, the softening starts at 100 degree, and essentially, like if you have PC, you get 140 degree. So I'm really curious how they you can actually have, like, are they going to, is there a kind of a cooling, how effective is that, or they have a mix of aluminum and plastic, so that you can sort of counteract all this effect, because the last thing we don't want is you train your model and everything, and then the arms start to bend and you suddenly lose precision, because essentially your body is now different, right? Like, if your arm is bending, it can be like 2, 3, 4, 5 millimeters, maybe up to 1 centimeter, and you also start to deform maybe your motors as well. If you don't cool them, yes, there are safety mechanisms, but they might actually damage themselves. So yeah, in general, and I have another tutorial about this, about materials and motors, but it's just a warning for now. Um, so what I'm going to do now, first of all, if you want to reach me out, reach me out on, I mean, you can go on LinkedIn or send me an email, but I'm going to switch now my browser just to see some of the things you can do. Okay, so now I'm back on their website. It's very nice. I like this kind of cartoonish things. As I mentioned before, they have, they have also other research, agentic model, um, alpha space, etc. But I went into their GitHub, and their GitHub have this, bunch of pictures. They talk about their legs. And so what I did, the first thing I took was the lower body. Okay. And so you can go here and you can see the actual joint for the foot, and you can, hide or unhide if you want to do things. You can actually see how the foot looks like. Usually if you look struck, I just go into isometric mode, which makes sense. You can zoom in and out. So yeah, that's the foot joint. As you can see, it's kind of like a linear actuator, a rotational joint, so this can go up and down. And I think this will give maybe definitely a more natural motion to the actual robot, but also more energy efficiency. As we walk, we start with, you have this kind of heel toe motion, which any other robot doesn't have. And so, yeah, this will be very interesting. Maybe we'll also be able to balance on an edge and do like calf raises, like you do in the gym. And so, yeah, that's the thing. That's the one of the main differences. And as I mentioned before, these are for the foot. And so, yeah, so the file is here. You can play with that. And if you have like Fusion, CAD, and other things, you probably want to use that. And yeah, so these ones are sort of open, so I guess it's to kind of see how the joints are moving, or just maybe for heat purposes. And I think this could be in metal or aluminum. I hope so, because for the heating things. But yeah, so this is the CAD. Then you can load this in the Mujiko viewer. So I'm using this Mujiko viewer. You can load the robot. And one of the things I mentioned is that the ankle joints, so you can play with that, right? So first of all, I can move the foot, look at that, 0 to 60 degree. Okay, makes sense. But when you go at the right toe joint, okay, that's the other one, fine. When I go to the ankle pitch, I can only go between, look at this, minus 20, let's say, minus 29 to 20 degrees. So it's not 70. So I don't know why they say 70 degree, which looks suspicious. And for the roll joint, you go between 5 and minus 5, right? It's not 70. So I don't know why on the website they say 70. I mean, I can go here and I can tell you they put 70 degree. So maybe it's the maximum theoretical on the motor, right? But yes, that's not 70, which makes sense. And then we have the joint on the knee. Yeah, so you can see you can go to like 80, 85 degree, which makes sense. If you go here, sorry, what is this? Yeah, 86 degree. Okay, 86 degree, that's fine. And you can see it doesn't go like, a human will go higher than that, right? Like, so I mean, I can definitely, I'm not super flexible, but I can definitely do more than that. But that's fine. And then they have the, as we mentioned before, on the knee, on the hip, you have the pitch, right? So it's, sorry, I touched the other one. Let's go on the left side. Can't even tell left or right. Yeah. So this is the pitch, right? Look at that. So notice how the this is kind of like a 40-degree, 45 angle. It's not going on a linear plane, so this is something you have to consider, right? Look at the swing, right? And then you have the roll, which is, yes, as you mentioned before, is going that, and you can swing. I'm doing the can't swing. Sorry, super funny. And then you have the yaw. So the yaw is essentially when you rotate your upper, or sort of the how do you call it? Well, the kind of hamstrings, right? The femoral. Um, so yeah, that's also pretty good. And then, well, you have the floating paste joint. I guess this it will be on the top. I don't know if this is rotating or is just a reference point. Okay, and then you have the other, yeah, the pitch, and so yeah, we have seen all of them, right? So if you compare that with a, what is that? Let me get a G1. G1 is already here. Okay, so as you can see, the actual food doesn't have that mechanism. And oof, let me see, where is it? Left, shoulder, pitch, ankle line. There we go. So this goes higher, it goes between 29, let's say 30 and minus 50. So a higher degree of mobility. And this one is minus 15 as well. So it does a little bit more than the Asimov. What else can we do? Yes, let's look at the, if you look at this one, where is the left knee joint? Sorry, that was the right. This one is, yeah, I am terrible. Right knee joint, there we go. Yeah, as you can see, there is pretty big a range here. Look at that. He can essentially touch the actual, the back of the muscles there. So, yeah, bigger degree of motions for sure. I'm not making things up. And the waist. So the waist is also interesting. Now look at the hip movement. Let's see if I can show you that. So the Unitree uses a 90-degree, right? Because if I go on the left hip pitch, this is a planar movement. Okay, it's not 45 degrees like Asimov is this one. So he will make it easier, I guess, to control. I mean, intuitively, if you're doing direct or inverse kinematic, they are orthogonal joints. And look at that. I mean, this guy is like, I'm not sure even a contortionist can do that. I mean, I've seen people in the circus doing all sorts of crazy things. Maybe it's possible, but he has definitely a greater range of motions. So there's definitely a collision there. But that means also you have to be careful when you do that because yeah, I'm touching the other leg. And let's see, this is similar, and I think they also do more here. There seems to be a full, 157 to minus 17. So overall, the Unitree has still a greater range of motion for sure. But like I think this 90-degree is have sort of more stress. If you think about when you're walking, right, you have this thing pointing at 90-degree angle, but if you have 45-degree angle, you can definitely absorb more energy, which I think why the Asimov have that kind of design. So I think your motors will thank you, although your controller will not thank you as is not a 90-degree orthogonal configuration. Of course, I can't tell anything on the top. I think, well, they have a waist. Yeah, so they can yaw, which I guess probably will have Asimov will have the same thing. But they also they can roll that way. And there's also a pitch joint. Yeah, so I think Asimov will have probably a similar mechanism there. So yeah, so this is just kind of a quick comparison on that one. For the motors, you can go here and you can check what they are, all the specs. I mean, it's annoying. There are images, not actual tables, and I can't find. Maybe there's a PDF here. I couldn't find a PDF. Maybe because I'm in the English version, so I'm not sure. Sorry, I should have gone Chinese. Maybe my Chinese is really rusty, but I don't see PDFs of some sort. So I don't know. Maybe when you ask for that, they will give you. So I think I've shown you everything. So that's the website, fully open source. You can go here, and there's the website, main website. Join the Discord channel, and if you want, go and pre-order. I wish I had that money. Well, thank you for listening to my tech rants, and hopefully we will give you some updates soon. If you want to reach me out, and if you want to be interviewed, or review of any other robot programs or projects, just reach me out. So with that, remember to like and subscribe. Have a nice day.